All right, let's get right into it. We're always hearing about how AI models are getting bigger, trained on just insane amounts of data. But what about the actual plumbing inside these models? The hidden highways that all that information travels on? That's what we're digging into today. It's a story about the search for a better, more stable information superhighway for AI. A tale of a really ambitious upgrade, a massive hidden flaw, and a surprisingly elegant fix.
So, for more than a decade now, the absolute bedrock of deep learning has been this thing called a residual connection. The easiest way to picture it is as a simple one-lane highway. It lets information from way back in the earlier layers of a network zip directly to deeper layers, kind of like an express lane that bypasses all the local traffic. This super simple design has been unbelievably reliable, and it's a huge reason we can even build these giant, powerful networks we have today.
Now, the secret sauce that makes this highway work so well is a principle called identity mapping. Basically, it's the golden rule that says the signal, our little car on the highway, has to arrive at its destination pretty much exactly as it started. It can't get crazy powerful and explode, and it can't just fizzle out into nothing. This one property is the fundamental reason our standard AI highway is so incredibly stable, especially when you build it out for miles and miles.
But what if you want more? I mean, that single, reliable lane has been great. But what if it's just not enough to get us where we're going, fast enough? Well, that's what brings us to the next big thing researchers tried, a really ambitious new design called hyperconnections. The whole goal was to build a much, much wider road. So the idea behind these hyperconnections, or HC, was honestly pretty straightforward. You've got a single-lane highway, let's turn it into a multi-lane superhighway. Simple. The thinking was if you create all these parallel lanes for information and, let them mix and mingle in interesting ways, the model should learn way more efficiently. You get better performance. More lanes, more power, better results. What could possibly go wrong, right? Well, as it turns out, something could go very wrong. This powerful new superhighway had a dangerous hidden flaw. You can think of it like a high-speed wobble that you don't even notice on a small test track, but becomes absolutely catastrophic when you scale things up for the big race. And this, right here, is the smoking gun. The researchers found that because the connections between all these new lanes were completely unconstrained, that all important identity mapping property we talked about just went right out the window. All of a sudden, the highway had no speed limits, no lane markings, nothing. Signals could get wildly amplified or just vanish into thin air, which, as you can imagine, led to total, complete instability. And when I say wildly amplified, how bad was it? Get this. At its worst, the signal amplification hit a staggering 3,000 times its original strength. Just imagine your car suddenly accelerating to 3,000 times its speed. It's not going to end well. You're going to have a massive, uncontrollable crash. And that's exactly what happened during training. The whole process would just destabilize and completely fail. Okay, so what do you do with a superhighway that's dangerously out of control? You don't just tear it down, you bring in the engineers. And that's where the hero of our story enters, Manifold Constrained Hyperconnections, or mHC for short. It's an incredibly elegant fix designed to tame all that chaos. The big idea behind mHC is basically to install a set of mathematical guardrails. Picture it like a perfectly engineered traffic circle that forces all the lanes to merge and flow together smoothly. This constraint makes sure that the total energy of the signal stays the same. So yeah, information can still be mixed and shared between the lanes, but it can no longer explode or just disappear. The traffic flow is managed, smooth, and predictable. And this image just shows it perfectly. On the left, that's the connection matrix from the original, unstable hyperconnections. It's a total mess, right? The values are all over the place, representing that chaotic, uncontrolled flow. But then look at the right. With mHC, the matrix is clean, orderly, balanced. You can literally see the stability that the mathematical guardrail brings. It is the perfect visual for chaos versus control. Okay, so the theory is beautiful and the solution looks super elegant, but does it actually work in the real world? Let's take a look at the results and see if these new guardrails can actually handle rush hour traffic. And the results are a clear, decisive win. This new highway doesn't just avoid the crashes. It actually gets you to the finish line faster and wins the trophy. The mHC model completely solves the instability problem, and it delivers even better performance than the original simple single-lane road. It's truly the best of both worlds. You get the speed of a superhighway, but with total stability. And here is the proof, right here in the numbers. Just look at that final column, the one for our fix, mHC.
I mean, across the board, it's just crushing both the original baseline and that flawed first attempt. But here's what's really cool. Look at the reasoning tasks, BBH and drop. That's not just a tiny improvement, that is a huge leap over the unstable mHC model. So this tells you the fix doesn't just, work, it absolutely excels.
So let's wrap this up. What's the big takeaway from our little road trip? Well, we saw how the big ambition to build a wider, faster road with hyperconnections completely backfired, creating a chaotic, unstable mess. But then, with a really clever and elegant mathematical fix, just a simple guardrail really, we not only tamed the chaos, but ended up with a system that's more stable, more scalable, and, ultimately, just plain better than where we even started.
And this whole thing leaves us with a really fascinating thought to chew on. This entire breakthrough came from simply rediscovering and enforcing a fundamental rule of stability in a more complex system. So it makes you wonder, right? If one simple mathematical guardrail can unlock this much more performance and stability, what other fundamental rules of architecture are we still missing? What other elegant solutions are just waiting out there to be discovered?